Alright guys, welcome back. I hope the first video lecture was able to help you understand and clarify some stuff. Now we're on to the introduction to conduction, which is chapter 2, and these video lectures are just supplemental to what your teacher is teaching you. And so in chapter 2, they introduce you to the conduction rate equation, which essentially, so in the first chapter, I introduced you to Fourier's law, or the heat transfer, which then introduced you to the heat flux, which can be denoted by the Q double prime. And so in my video, you're going to see this big Q double prime, and for the editing on there, it wouldn't let me go to a lower Q due to the bullet points. But this the heat flux is also equal to the heat transfer divided by the area, which is equal to the negative thermal conductivity times the temperature gradient with respect to x. And so, as I said last time, the heat flows perpendicular to, normal to the cross-sectional area, and it can be more generalized as the heat flow will always be normal to the surface, to a surface at constant temperature, or an isotherm. And so then you can see that there's the possibility that that this can be three-dimensional, and so it can be expressed. This heat flux can be expressed as a vector quantity, which can be seen here, which is right here, the negative k with the temperature gradient. They just factored it out with respect to x, the temperature gradient, the change in temperature with respect to y, and the change in temperature with respect to z. And so, sorry, that k shouldn't be there. And so this implies that it's normal to a surface at constant temperature, or the isotherm. So you can also express it, another expression for the heat flux is this Q double prime times N, which then you get the negative thermal conductivity times the change in temperature with respect to the normal direction, and this little n times this n, and this little n is a unit vector in the n direction, and the Q double prime is the heat flux in the n direction, which is the normal direction, which is normal to an isotherm. So as you can see here, there's this, let's just say we have this isotherm right here, and so the heat flow would flow perpendicular to it. And so when it's perpendicular, you can break it into components. You can have a heat flux of the x component and the heat flux in the y component. And so that means the heat flux can be expressed in components as well. And so you can get a heat flux x, which is equal to the negative, sorry, I forgot to add that, thermal conductivity times the change in temperature with respect to x, and then the heat flux in the y directions, which is the negative k times the change in temperature with respect to y, and then the same with z, but just with respect to z. And so this implies that the heat flux implies that the material is isotropic. And so by isotropic means it's kind of the way that the grain boundaries flow. So in anisotropic, the materials kind of have a direction with it, whereas isotropic, it's non-directional. And so this implies that k is independent of a coordinate system, or it's independent of the x, the y, and the z, and that's why you can factor it out up here. You can factor out the k because it's independent of those coordinates. And so the Fourier's law is a vector expression indicating that the heat flux is normal to an isotherm, which is just basically a surface at constant temperature, in the direction of decreasing temperature. And so next, the book goes on and it explains the thermal properties of matter, and it starts to talk about thermal conductivity. And I kind of went over this in chapter 1, and the thermal conductivity depends on the physical structure of matter, the atomic and molecular, which is related to the state of matter. So like solid, liquid, or gas, or there's also plasma as another state of matter. But we're just going to deal with solid, liquid, and gas in this book. And so the thermal conductivity has a trend to it. So the thermal conductivity of solid is greater than thermal conductivity of liquid, which is greater than the thermal conductivity of gas. And as you can tell, or you kind of notice, this trend is due to largely the differences in the intermolecular spacing of the two states. And so, like, for example, the solid state, which is the solid can be comprised of free electrons and atoms bound in a periodic arrangement called a lattice. And this is a material science discussion right here. So you can have BCC or FCC, which is body center cubic. And so it's just a different way of classifying the arrangement of the atoms in a lattice. And so in solids, the thermal or the heat transfer energy is due to two factors: the migration of free electrons and the lattice vibrations, or the phonons, which the migration free electrons is mainly in conductors, and the lattice vibrations plays a big role in semiconductors and insulators. And so we can express the thermal conductivity as an actual, as we said, it is material dependent, but we can express it as a formula. And so this formula is derived from the kinetic theory, which yields the 1/3, the C bar, and lambda. And so the lambda is the electron mean free path for conductors, which is defined as the average distance traveled by an electron before it collides with either an imperfection in the material or with a phonon. And so then the C bar is the mean electron velocity, and the C is the electron specific heat per unit volume. And so as you can tell, that as the lambda, or the electron mean free path, increases, the thermal conductivity is going to increase. And so as all cases, the thermal conductivity increases as the mean free path of the electron carriers is increased. So as the distance traveled by the electron before it collides with something it becomes longer, that's going to increase the thermal conductivity. Oops.
As I said in the first chapter, the thermal conductivity is broken into, dependent on two components, which is the thermal conductivity of the electrons and the thermal conductivity of the lattice vibrations, or the phonons. And in metals, the electron thermal conductivity is dominant, and it's inversely proportional to electrical resistivity. And in non-metals, such as semiconductors and insulators, the phonons are the dominant thermal conductivity. And so the thermal conductivity is temperature dependent, and for the most part, as you increase the temperature, it's going to decrease the K, or the thermal conductivity value. And these properties are not all the same, or the thermal conductivity is not the same for a nanoscale material. So if you have, it differs from the bulk material. So what I was talking about up here for the solid state is going to be different for the nanoscale. And so as the material becomes thinner, the physical boundaries of the material can decrease the average net traveled by the energy carriers. So the physical boundaries act to scatter the energy carriers, or the phonons, or the energy carriers, I mean the phonons and or electrons, and redirect their propagation. And so as you can see right here, hold on. As you see right here, this can be represented the bulk material, and this can be represented the nanoscale material. So this is Y, and that is X in both pictures. And as you can tell, this one is bigger and this one's smaller. I mean, and so as you decrease as you make it thinner, these physical barriers, or the walls, play more of an important role. Whereas in the bulk, they are negligible. But as you can tell, in the, these walls will play more important part or role. And as you can tell, there's different thermal conductivity values. As I said, it can be broken into components. So the thermal conductivity, or sorry, I said heat transfer, but the heat flux. But the thermal conductivity can also be broken into components. And so the thermal conductivity in the X value for the nanoscale is going to be smaller than the thermal conductivity in the Y value, because as you see, you have more space before you hit a wall. And so once it hits a wall, it's going to scatter and redirect the propagation.
And so the thermal conductivity in the X direction is going to differ than that in the Y direction. And so the X direction thermal conductivity for nanoscales can be given by the thermal conductivity in the X direction divided by the thermal conductivity of the bulk, which is equal to 1 over lambda, which is the energy carrier, or as I refer to it as the electron mean free path, and divided by 3L, which is the length of the material. And so the Y is going to be essentially the same formula, except it's going to be 2 lambda divided by 3 pi L. And so these two equations only hold true if the ratio of the length to the energy carrier mean free path, or electron mean free path, is greater than 1. And so the small grain boundaries act as the actual physical barriers that lower the energy carrier mean free path, or the electron carrier mean free path. And so that's what lowers the thermal conductivity in the nanomaterial. But the nano scale material still has greater most have greater the thermal conductivity of metals still usually have a greater thermal conductivity than that of the fluid state. So the fluid state is less effective in the thermal conductivity. The kinetic theory yields an actual formula for the thermal conductivity, which is given by approximately by 1/3 the density of the fluid times the specific heat. Oops, sorry. Come on. Alright, close enough. Times the molecule speed, or the molecular speed, the mean molecular speed, times the lambda, which is the energy carrier mean free path. And in this case, the energy carrier is the molecule, not the electrons or photons in this sense. And so once it gives you the formula for the energy carrier mean free path, and so once you plug that in, you obtain this answer over here, which is given by the Y in this here, right here, this Y is the ratio of the specific heats, the N is the Avogadro's number, and the Kb is the Boltzmann constant. And so this is very important to note that it's independent of pressure except near perfect vacuum. And so there's relevant properties that we use throughout this book that are good to note, and one being the density times the specific heat, which is called the volumetric specific heat, or volumetric heat capacity, and that's given by the density, or rho C, in the specific heat of the material. And another one is the thermal diffusivity, which measures the ability of the material to conduct thermal energy relative to its ability to store thermal energy. So it's kind of like capacitance in electronics. And so the thermal diffusivity, which is denoted by alpha, is the thermal conductivity over the volumetric heat capacity, which is the density times the specific heat. And so large thermal diffusivities will respond quickly to thermal environments, whereas small ones respond sluggish. And so now we're going to derive a very important equation that will help you in conduction. It gives you the three-dimensional. Okay, so now we're going to apply the heat diffusion equation. So heat diffusion equation. And so to begin, there's going to be no bulk motion, no change in mechanical energy, and no work done on the system. So, and there's only going to be thermal energy if there is a temperature gradient present. So if one side of the wall is hotter than the other. And so we're going to apply the conservation of energy to a differential control volume. So it's going to be, the control volume will have a volume of dx times dy times dz. And we're going to use what we did in 1.3, which is the E in minus the E out plus the energy generated equals energy stored. And it's going to be on a rate basis. Remember, the dots mean rate. So heat diffusion. And so to begin, we're just going to take a differential control volume, so just a little piece of the entire material, which can be seen here. And so what's going in the system is going to be in, remember, these heat transfers have to be normal to the surface of which it's going. So there's going to be heat transfer going into the surface in the which is perpendicular, so it's going to be the ZY plane. So it's going, we'll call that Q of X. And what's going out is the Q of X plus some, so Q of X plus some differential control volume of heat flux. And so also what's going in is the Q of Z on the X and Y plane, and what's going out is the QZ plus the DZ. So it's that, again, that little differential heat transfer that goes out. And so there's going to be a Q of Y as well. So I wrote down what's going in right here. So you're going to get Q of X, Q of Y, and Q of Z. And what's going out is written here. And it's going to be the Q of X plus some partial Q of X with respect to X. And same with the Y and the Z. So you're going to get the Q of Z plus the partial heat transfer with respect to the Z direction. And then you'll get the Q of Y plus the change in heat with respect to the Y direction. And so we also need the energy stored, or the energy generated, which is given by this Q times dz, dy, dx. And this Q dot stands for the heat transfer per volume. So it's going to have watts per meter cubed. So when you multiply this differential control volume by it, so by meters cubed, you're going to get just watts, so you get the heat transfer. And so the energy stored is going to be the volumetric heat capacity, so this density times the specific heat, times the change in temperature with respect to time. And so when you apply the equation that we learned in 1.3, which right here, so you apply this equation, you get this right here. We're going to circle it. So you get this. So you get the Q of X, Q of Y minus the QX, DX, and then the QY, DY plus the QZ, DZ, plus the energy generated plus equals the energy stored. And so when you simplify it, you're going to get this partial heat transfer in the X with that, heat X, minus the partial Q of Y, minus the partial of the heat transfer in the Z with respect to the Z, plus the energy generated, which is given by the Q dot times the differential control volume, which is equal to the energy stored. And so, as you can see here, so this right here, this equation, so you get QX, QY, and QZ. So these terms are canceled out by these extra terms. And as I said, I wrote them down right here. So remember, this is subtracting. So this is going to cancel with this one. This Q of Y will cancel with this Q of Y. This Q of Z will cancel with this Q of Z because the out is being subtracted. And so, again, when you do that, you get this equation, and you simplify everything, you get this equation right here. And so the heat transfer in the x direction is equal to this. So you get your k times the temperature gradient with respect to x times this dy dz, that is the area. And so you're going to plug these q of x into that q of x up there. So I'll give you an example. I'm not going to write out the whole entire equation. So you'll get, so we get the, remember it's negative. We're just going to, we'll do the q of x one. So times negative k dy dz, because it's perpendicular to the heat flow in the x direction. So that's the area that's perpendicular. So that's area times the temperature change, or the temperature gradient in the x direction, all respect to, where is it? Respect to x, dx. So that's what happens when, and you can plug that in, and then the y, so if you get q of y, this would be x instead of y, and these will be y's right here. So everything would just be respect to y instead of x. Okay? And so what happens next is that when you plug in the appropriate q, you'll get this equation right here. I'm going to erase some of this stuff. So, all right. So you get this equation. And so essentially what we did is we just divided out the control volume. And so the control volume is going to stay the same in here. And so you can essentially pull it out and it becomes this, which is, remember the negatives cancel as well. So you're going to get positive k with the change, or the temperature gradient in the x direction, or with respect to x, times the, times the dx, dy, and dz. So we'll denote that as is equal to dx times dy times dz. So you get that. And as you can see from up here, so each one of those q's are going to have that. So the dy, sorry, the partial of the heat transfer with respect to y will have this differential control volume. Same with the x, or same with the z, and same with the x. And as you can see, the q dot has it right here, and I forgot to add it up there. So and so I forgot to add this right here. So it's going to be q x dy dz. So they all have it. So you can just divide it out. So when you divide everything out, you'll get this equation right here. This. And so it can be seen better by this bolded statement right here. And there's different ways you can simplify it. Sometimes they use 1 over alpha, which is the thermodiffusivity. And so, and right here they divided everything by the k. And so remember the thermodiffusivity, which is written up here, which is k over this volumetric heat. So alpha equals k over the specific heat times the density. So that's where that k comes in. You're like, oh, well, where's the k? Well, it's in this diffusivity term. And so to better utilize the heat transfer equation, we are able to apply boundary conditions, because this is a second order partial differential, and this can be cumbersome to solve. And so these boundary conditions allow us to get rid of some components to it, and we'll better utilize the equation. And so the first one they give us is when the surface is at constant temperature, and this happens when when the surface is in contact with like a melting solid or a boiling liquid. In both of these cases, the surface remains at the temperature of the phase change process, so it's at a constant temperature. And so the temperature is a function of both time and position. And so this happens at any given time, but at the initial position or at the surface, because that would be the initial position of the material. So when that happens, so at any given time, it always has to be at the initial position. It's going to be Ts, which is going to be the surface temperature. Another case happens when there is a constant heat flux, and so the heat flux is generally can be a function of position. So at the initial position, so if there's the surface is at constant temperature, so at the initial position, it's going to be equal to negative K. Let me get rid of that. All right, let's go there. So it's going to be negative K, and it's going to be the change in temperature with respect to X and at the initial position, and that will equal the surface flux, surface heat flux. And so this happens when like a thin film, like electrical heater, is applied to the surface, so it maintains that heat's being applied to it. And so a special case of this happens when there is an insulated surface on there, or on the surface. And so when that happens, there's no change in temperature, so at that initial position, so when that happens, it's the change in temperature with respect to X, or whatever direction you're applying this in, is going to be equal to 0 at the initial position, because there's no change in heat. And so thus that implies that the heat flux, is equal to 0 as well, because of the equation. So if you were to plug it into this one, so negative K, and this is going to be 0, that means the whole entire equation is 0. And so the last condition happens when there's a convection at the surface. And so this happens, we obtain this equation by a surface balance, so kind of like what you've previously seen. And so it's given by the temperature or the heat flux at the surface, so at the initial position, is equal to the heat flux of the air minus the temperature, the surface temperature. So remember, the temperature is a function of both the depth into the material, or X, and time. So at any given time at the surface, so at the initial position. Because the further you go into the material, the further X is in this situation, because it could also be different directions as well, so it could be Y, but we're just for X. And so it's going to equal essentially the surface temperature, because it's at the initial position, which is the surface, at any given time, minus, the air temperature minus the surface temperature at any given time, is equal to the heat flux at the surface. And so these three boundary conditions allow us to better utilize the heat transfer equation. And so now I'm going to just discuss a few of the problems and go over them with you, and I will continue that in the next videos.